Welcome back to my channel. This is part 8 of our Introduction to Calculus series, and today we're exploring indeterminate forms. Let's get started. So far, we have looked at 2 indeterminate forms. In this video, we'll explore the others. Let's start with this example. If we plug in the value directly, we get the form 0 raised to power 0, which is indeterminate. But why is it indeterminate? Because we don't know which part dominates, the base or the exponent going to 0. Depending on how fast each one changes, the result could be a constant, 0, infinity, or the limit might not even exist if the function oscillates. Just seeing 0 raised to 0 isn't enough. We need to analyze the function more carefully to find the actual limit. So, how do we solve this limit? Let's look at the function on its own and apply the natural logarithm to both sides. Now we'll need to use some logarithmic rules we learned earlier. Let's start with this one. We can rewrite it as a fraction. This gives us the indeterminate form infinity over infinity. So we can apply L'Hopital's rule. Let's take the derivatives of the numerator and denominator and simplify it. This means this limit is 0. Remember this rule? Replace y by x raised to x and ln of y by x ln of x. Apply the limit. The limit of this power is 0. So, the result is 1. This function is very similar to the previous one. However, in this case, the base approaches 0 as x tends to infinity, while the exponent grows without bound. This creates this indeterminate form. It's considered indeterminate because the result depends on how fast the base approaches 0 compared to how fast the exponent increases. If the base shrinks faster, the whole expression may tend to 0. If the exponent grows faster, the result may diverge. They might also balance each other or oscillate. Therefore, we need to use a method like the one used previously. Consider the function in this equation and apply the natural logarithm to both sides. Use the following logarithmic rule, and also this rule. Then, apply the limit. We know that both x and ln of x tends to infinity, so this limit is minus infinity. Once again, we need to use this rule. Replace y and ln of y. Apply the limit. The exponential function tends to 0, as x tends to minus infinity. So the result of our limit is 0. Let's keep going with the same limit. What happens as x approaches 0? In that case, we run into another indeterminate form, infinity raised to 0. The initial steps of the solution are the same, so let's jump to this limit. What happens to the logarithm as x gets closer to 0? The logarithm heads off to negative infinity. So we get the indeterminate form 0 times infinity. And once again, it's unclear which part wins, the shrinking x or the growing ln of x. Let's start by solving this limit. We'll rewrite the product as a fraction so we can apply L'Hopital's rule, as this is a well-known indeterminate form. Remember these derivatives? The first one is straightforward. The derivative of ln x is 1 over x. As for the second one, we need to apply the power rule. Rewrite as x raised to negative 1 and apply it. Simplify this expression. Replace x by 0 to find the result. And there it is. The limit is 0. Now that we've worked out this limit, let's go back to the original one. Since e raised to 0 is 1, that means our final result is 1. Let's now talk about an indeterminate form that, at first glance doesn't seem indeterminate. Consider this limit. If we apply substitution, we get the form 1 raised to infinity. But why is this considered indeterminate? After all, we know that 1 raised to any power is always 1. Well, not quite. Remember, we're dealing with limits. The base here isn't exactly 1, it's approaching 1. It could be slightly greater or slightly less. And yes, the exponent is going to infinity. So the real question is, which one grows faster? The base approaching 1 or the exponent heading to infinity? Depending on that balance, the result could be 1 or any other number. It could even be infinity, or the limit might not exist at all. In this particular case, the result is the famous Euler's number. As for the full solution, let's save that for the video dedicated to this special number. For our final indeterminate form, let's consider the following limit. It's easy to see that both the square root and the term x tend to infinity as x tends to infinity. Since we don't know which one grows faster, this is an indeterminate form of type infinity minus infinity. To solve this limit, we start by multiplying and dividing by the conjugate. In the numerator, we get a difference of squares, which simplifies the expression. Then, we divide both the numerator and the denominator by x, and simplify it. As x tends to infinity, 1 over x tends to 0. Therefore, the limit is 1/2. And that concludes our lesson. If you've learned something new today, make sure to like the video and subscribe. I'll see you in the next video.